Welcome and good morning, everyone. My name is Jeffrey Horning. I am a senior political scientist and RAND's lead on Japan. And I'm very happy to welcome you all, both in person as well as the large audience that we have joining us virtually today. This is the fourth iteration of RAND's US-Japan series that's focused on issues on economic and social well-being. Previous conferences in this series have focused on things relating to space, artificial intelligence and machine learning, and cryptocurrency. As this brief snapshot of these past topics illustrate, the series has highlighted some of the most pressing issues that are facing mankind. And to discuss them, we've been fortunate over the years to bring together a stellar group of experts in their field to provide both their insights on the opportunities as well as the challenges for both the United States and Japan. Today is no different. As all of you know, the focus of today's event is on quantum. Quantum technology is a field of science that is still relatively new, but it offers new ways to measure, store, process, and transmit information that move far beyond what existing technology can do. Quantum is exciting, and it promises to affect every aspect of our lives. Examples include the ability to create unbreakable encryption, unhackable communications, help design and develop new drug treatments, help create more reliable navigation and timing systems, support online purchases through more secure transactions, find more efficient methodologies for financial services and shipping goods, and carry the potential to process vast amounts of complex data for machine learning and more advanced computing technologies. What all this points to is quantum technology not just revolutionizing our world, but making one that is more efficient, more secure, and able to address today's complex problems with unthinkable immediacy. In some ways, the dawn of mankind's quantum future is only just beginning. Several models of quantum systems exist, and each has strengths and weaknesses. Companies and universities across the globe, particularly in the United States and Japan, are in the experimental phase with different models. While it's true that you do not need to be a quantum engineer to benefit from the technology in the years ahead, there are no doubt many questions on what the future will look like and the types of challenges that we can expect along the way. And that brings us to today's event. As all of you no doubt know, RAND is not a laboratory, nor do we focus exclusively on science at RAND. And yet the interest of RAND to host an event like this fits squarely in our organization's goals. RAND is a nonprofit research organization that develops solutions to public policy challenges and helps make communities throughout the world safer and more secure, healthier, and more prosperous. This is exactly why we're hosting this event today. With a stated focus to help improve policy and decision-making through research and analysis, hosting an event like today's offers an opportunity to better understand quantum. Quantum technology may be the next technology to fundamentally change the way we work in every field of our life, which makes it critical for policymakers to better understand the benefits and challenges of the technology and be ready to respond to its rapid advances. Now, while the focus of today's event is quantum, we are also highlighting the partnership between the United States and Japan. While industries and universities in both countries make strides in the field of quantum, it is also critical to recall that the governments of both our countries signed the Tokyo Statement on Quantum Cooperation in December 2019. Providing a framework for like-minded countries to cooperate on the advancement of quantum information science and technology. Echoing this statement, which declares that international partnerships are critical to bringing together the wide range of skills, expertise, and ingenuity to accelerate the research and development in quantum, today's event is meant to bring together experts from sectors in both the United States and Japan to better understand where the field is today and where it's moving in the future. Let me close by providing my gratitude and thanks for today's partners, Japan's Consulate General in Los Angeles, and the Japan House, Los Angeles. We at RAND are honored to continue to have a great relationship with these stellar partners, allowing us to together showcase the best that the US-Japan relationship has to offer. In that vein, let me turn to each of our partners to offer a few comments before opening it up to today's events. Our first speaker is Consul General Sone Kenko. Consul General Sone arrived in his post in 2021, and has come to RAND, I believe, 2 times prior to today, but this is the first time welcoming him for an in-person event like this. We at RAND are always happy to work with him and the consulate and our mutual support for an ever-strengthening US-Japan relationship. Consul General Sone has an impressive background in the foreign ministry, which he entered in 1989. Over the years, he has not only held numerous overseas posts in India, Switzerland, and 2 stints at the US Embassy in Washington, D.C., he has also held numerous posts in Tokyo, including the North American Affairs Bureau, the Asian and Oceanian Affairs Bureau, and the Economic Affairs Bureau. His immediate postings prior to joining us here in the United States were that of Assistant Minister, Director General for Cultural Affairs, held concurrently with being Ambassador in charge of Sport and Budo. Consul General Sone, the floor is yours.
Thank you, Jeffrey. Thank you. Welcome to this seminar. My name is Kenko Sone. I'm Consul General of Los Angeles. As Jeffrey mentioned, that I just arrived in September 2022, and I've been here already twice just for the seeing the RAND Corporation. But actually, I even come here before that in 2020. 2000, I think it's 15, when I was working in the foreign ministry in Tokyo, dealing with Japan-US relations under this office. And our relation with RAND is really closely, and especially seeing this very difficult global situations, the RAND, insight and the analysis is always helpful for the Japanese government also to think about the future as well. And I also would like to thank the archive-san to join this seminar. Japan House Los Angeles is located in Hollywood, and she's been really always supportive of our collaboration culturally, and also the more like the broader Japan-US relations as well. So today's topic is quantum science research. Of course, it is one of the fields currently drawing most attentions, with various countries also enthusiastically conducting research and development. Japan is also closely watching the field for its potential wide use applications across different areas in the future, and because of its essential role for the future, our society of our future. And the cooperation between Japan and the United States in this field is also currently very extremely important. Now it's we are not only talking about technologies, but also talking about the strategy or the economic security issues. So those technology is going to be very important, not only for the benefit for the society, but also in a sense related to security issues as well. And so in addition to the research and development, it is very essential for our nation to work together to explore how the field can be adapted for our actual use in the future. And in this morning session, we expect the panelists to explain the current results of the fundamental research in this field. In the afternoon, we're expecting speakers speakers coming from different fields, including business engaged in the cutting-edge tech initiatives. Will showcase the current status of this development of this quantum technologies. Well, its content, I'm not a scientist, so its content might not so easy to understand. But at the same time, this field is really important for our future. It will benefiting the society, and so therefore it is also important for us to understand the current situation, how it really used for our future of our societies. So I hope the speakers, the panelists will share with us the interesting aspects, attractions, and appeal of this field in a way that a little bit easier for people like me to understand. And then finally, I'd like to express my sincere appreciation for Jeffrey and Teddy Brand, who's had their hard work made this seminar possible. And also today's distinguished speakers, panelists for joining us. And I'm very much looking forward to hearing from your perspective of this quantum technology. Thank you very much.
Next person I'd like to ask to come up for a few remarks is the president of the Japan House, Los Angeles, Kaifu Yuko. President Kaifu, welcome back to RAND. It's been some time since we last welcomed you here, but always happy to have you come back. For those of you who do not know, the Japan House is a gem of an institution. And we are fortunate here in Los Angeles to have it, as there are only 3 of these worldwide. Japan House seeks to foster awareness and appreciation for Japan around the world by showcasing the very best of Japanese art, design, gastronomy, innovation, technology, and more. President Kaifu joined the Japan House in January 2016 to start the organization. She started her career at Japan's Ministry of Foreign Affairs and has had assignments that included the Embassy of Japan in Canada, the Consulate General here in LA, and various departments in Tokyo. After leaving government service, President Kaifu worked at the Japanese American National Museum as the vice president, and later at MUFG Union Bank as a managing director of corporate communications. Again, we're very fortunate to have President Kaifu lead such an impressive organization to help showcase the best Japan has to offer here in the LA area. It's my pleasure to welcome President Kaifu.
Good morning, everyone, and thank you, Jeffrey, so much for your kind introduction. It's a great pleasure for us to be able to work with RAND Corporations again. We've worked with you a few years ago in person, but we've also co-hosted some webinars as well. But it's always great to come back here and see the full house of people like you to do this very significant program this morning and this afternoon as well. Now, I was going to talk a little bit about Japan House, but you've already covered it, Jeffrey. But then, yes, we're located in Hollywood, and we do all kinds of programs, including exhibition. The most recent one was a Pokemon meets Koge, Japanese craft. It was really widely popular, and we're going to start the new one at the end of this month, featuring 6 regions in contemporary design. In those regions. If you're, and we also do programs as well, like tea, workshop, and shojinrori, culinary, all these kind of things. So if you're interested in Japanese art and culture, you wouldn't regret it if you come. Even if you are not interested, please come. Because if you want to focus on your science, technology, research, our programs give you some, release your tension and give you some mindfulness. So we're looking forward to seeing you there as well as here. We want to do more programs here. Now, as you can guess, I'm not a scientist. I'm not from the natural science side of it, but I know that with the advance in technology and science and technology, I know that you can't afford to say it's their work, it's your work, it's not mine. Because it's the advancement of technology impacts our daily life so much. My son happens to be at Caltech wrapping up his PhD in applied physics this year, hopefully this year. So he sometimes fills me in with some aspect of science and technology, but it still sounds so alien, foreign to me. So I'm looking forward to listening to the speakers today and get some, so that I get some connection between science and technology, quantum physics, quantum technology with daily life. I have to repeat the request from Consul General Sone to the speakers today. Please be easy on a layman like myself. Looking forward to learning much about the theme today. So thank you so much for having us.
Thank you very much, both of you, for those remarks. So let me now turn to the first panel. The first panel is titled Fundamental Research in Quantum Science, Deepening Our Understanding of the Universe. For this, we have assembled 4 excellent speakers who will help us understand what is being done both in university and private industry. I'll not provide their full bios right now. I do encourage you, if you have an interest in one of the speakers, to please look at our event page online where you can read a more detailed bio of our speakers. We will begin today's panel with Dr. Eric Hudson. He is a professor of physics and astronomy at the University of California, Los Angeles. In addition to being the founder and co-director of the UCLA Center for Quantum Science and Engineering and a co-director of the NSF Challenge Institute of Quantum Computation, Dr. Hudson also founded the UCLA Master of Quantum Science and Technology degree program. Our next speaker will be Mr. Kazugomi, President and Chief Executive Officer of NTT Research, which is the global R&D arm of NTT. As many of you know, this organization was established in 2019 in Silicon Valley to conduct basic research in physics and informatics, cryptography and information security, and medical and health informatics. Before assuming his current position, Mr. Gomi was a board member of NTT Communications and led NTT America in New York as its CEO for more than 9 years. After Mr. Gomi, we will ask Mr. Rikuto Fukumori to speak, PhD candidate in applied physics at the California Institute of Technology. Mr. Fukumori is doing experimental research in developing quantum technologies for quantum networks. Originally from Tokyo, Mr. Fukumori is interested in facilitating collaboration for quantum communication research among nations and hopes to use his expertise in this field to eventually contribute to the construction of quantum communication link, for example, between the United States and Japan. Our final speaker will be Dr. Pranaya Narang, professor in physical science at the University of California, Los Angeles, with an interdisciplinary group spanning areas of physics, chemistry, and engineering. Dr. Narang is also the founder and chief technology officer of Aliro, a VC-backed US quantum company network. Prior to moving to UCLA, she was an assistant professor of computational material science at Harvard University. And then finally, all sessions today will be moderated by my RAND colleague, Dr. Edward Parker, who is a physical scientist here at RAND. Dr. Parker's research focuses on emerging technologies with a particular focus on quantum technology. And he has published several reports performing comparative assessments of several nations' efforts in quantum technology and analyzing challenges in adopting next-generation cryptography systems that are resistant to attacks from quantum computers. With that, we can now start the panel, and I'll turn it over to Teddy.
Thank you guys for having me here. I'm an atomic physicist at UCLA, and I'll causing audio problems. And I thought, what would I talk about to such a broad audience? And I thought, I've been thinking a lot about this question of what is the role of academics like me, given this quantum revolution that we're, living through. And related to that, what's the role of government? And so what I mean by that is, if you take the backdrop of all these companies, IBM represented here today, Microsoft, maybe one of the most valuable companies in the world, Google, companies like Quantinuum, they're investing billions of dollars. They employ thousands of people working on this. And if you come to my lab, there's like 10 or 15 people in a basement, scratching out a living. So what is it that we can do to contribute, or should we just get out of the way at this point and let industry, bring this to market? The answer to this question, at least for me, is encapsulated in this curve, which I'm sure you've seen before. This is called the Gartner hype cycle. And it's sort of what happens when any new technology comes about. There's something that triggers the technology. This axis is time. This axis is sort of how visible is it, how many people care about it, how many tweets there are about it. And what you see is there's some technology trigger, maybe that was Shor's algorithm, maybe it's something more recent with, the development of some technology. People get really excited about it, and then we realize this is actually really hard. And so we hit this peak of inflated expectations where quantum's going to solve everything, and then we realize, okay, we actually maybe have another 10 years of work here, or maybe more. And people get disillusioned with it, and then eventually you come out. I worry about this curve for the following reason. If you go look at something like AI or machine learning, which went through this same sort of process, there was an AI winter, right, several times. We eventually got out of it because GPUs became really powerful, right? So, how did we get out of this trough? Well, computers just became really powerful and we could run the algorithms. That's exactly what will happen for quantum if we get into this sort of trough, is like, we'll need better technology to come about so that we can, deliver the quantum computers of the future. But unlike machine learning, where pretty much all of humanity agrees faster computers are better, right? So that technology, there was a lot of sectors that wanted to develop faster GPUs, right? Faster computer processors. There are not that many people besides me and, some companies that care about, long coherence time qubits or, modular acousto-optical modulators, like all these sorts of really specialized technologies. They don't really have a lot of applications outside of that. So if we get in this trough, what I sometimes call the quantum winter, I worry that it can really affect the progress of the field. It may take us longer to come out of this, this trough, and it may not be guaranteed even. So I see the role of academics, and I also think the role of government is to try to help build this bridge. Like, we absolutely have to rely on industry to commercialize this. Like, academics are terrible at that, right? Government is not good at that, but industry is good at it. But there's a lot of work to be done to sort of get through this trough. This is assuming something like, for the experts, that there's not some near-term NISC application that's discovered that just lets us jump over this, which I hope is true. But nonetheless, we're going to have to deal this bridge. Academics can do it with fundamental research. Government needs to be prepared to step in at that point with funding to help companies survive this if it happens. Okay, so with that, I was asked to say a couple words about what it is I do, and I'll do that super quickly. Within this backdrop, our group works on two things, which is what we call higher fidelities and new paths to scaling up. So in quantum computing, we have some qubits, these quantum bits. We want to do operations to them, just like, we'd have bits in a classical computer and we do operations to them. When we do those operations, we want the thing to happen exactly as we will, tell it to happen. In a classical computer, the error rates are like 1 in 10 to the 30, right? You tell a bit to go from 0 to 1, it's going to happen, right? In a quantum computer right now, those error rates are more like 1%, or, 0.1%, 0.01%. And it's correcting those errors is a big part of realizing what we call fault-tolerant quantum computing. So my group's personal goal is what we call 4 nines fidelity in all primitives. What that means is to show that we can do all the quantum operations where we only make 1 error every 10,000 times, right? We're not there yet, but we're actually pretty close. And this is sort of the benchmark we've set for ourselves, because at this level, things like quantum error correction, which you may have heard about, become somewhat realistic. We also work on what I call new paths to scaling up. That is the other challenge of quantum computers, right? They're noisy, and so that's the fidelity aspect of it. The other part is, right now we have hundreds of qubits, and we need, we'd like to have billions or millions or trillions of qubits someday, right? So how do we scale that up? We work on what I would call not mundane, but straightforward things. Like, a lot of the qubits we work with require lasers to be manipulated. So just like we have electronic circuitry, we're working on building photonic circuitry where you can route photons just like we run wires on a chip to control these qubits. Another thing that we work on is what I call sort of the ultimate limit of nanofabrication, right? What is the ultimate limit of nanofabrication? And the answer is chemistry, right? Chemistry is assembling, molecules atom by atom, and using using chemistry to try to build up quantum computers. And so this is the kind of stuff where, industry can't do this because, the chances of it working are not high enough to get anyone to invest in. But in academia, this is, how we can contribute. Okay. Let me just say a little bit more about these two things before I close with something else. So this quest for higher fidelity that I was telling you about, if you know about the field, there's a company called Quantinium, and I should just say I consult for this company, so I am somewhat biased. They have this really amazing ion trap quantum computer. So on this little chip, you can sort of see these electrodes. They trap single atoms, and they can move the atoms around. They can interact with them with lasers and electric and magnetic fields. And what you do is inside those atoms, right? You all know from your chemistry class, atoms have internal states, right? Like these electronic states, or they have spin. We can store information in those levels. If an atom is in one state, that's a 0. If it's in the other state, it's a 1, and it can be in superpositions, that's a qubit. Right? And so they're sort of the perfect qubit in some way because they're nature's qubit, right? And they're all identical. We can shuttle them around. We can talk to them with lasers. And when you see something like this, you might be tempted to conclude, well, atoms are very simple. Humans understand atoms perfectly. There's really nothing left to be done but engineering at this point. We need to integrate and scale up, right? And some folks will say that, that the physics of quantum computing is done, but the physics of quantum computing is not done. And that is a very important thing to remember. There's still much basic science to be done, even for a system as advanced as this. Very simple questions like, what are the best atoms to use? What are the optimum states inside of those atoms for storing and manipulating that information? Can you leverage the complexity of the atom for things like error correction? And even what are the fundamental error rates? These are all open questions, right? These seem like the things that should have been answered 20 years ago, but they're not. I'll show you one sort of vignette, I suppose, into work I do with this guy, Professor Wes Campbell at UCLA. He's a brilliant atomic physicist and a partner in crime and many things. And this was a few years ago. We got interested in this very simple question: is what is the best atom to use in these quantum computers? I mean, there are already quantum computers out there. Surely this question was answered. And it turns out the answer had not yet been delivered. And maybe we still don't know. But what we found working in a basement with a couple grad students was that there was a certain isotope of barium, right, just an atom you've heard of, that is now called the Goldilocks qubit. No one had ever used it. No one had ever even addressed it with lasers in one of these traps. We were the first to trap it. This is actually the first ever picture anyone ever took of one of these atoms. And we demonstrated the basic quantum primitives. And so this is just, fundamental science. A couple of years later, IonQ, which is, a publicly traded trapped ion quantum computing company, has announced that they're changing to barium. That's going to solve quantum computing, and their stock price jumped considerably, right? Of course, I didn't see any of those dollars, but it's fun. So this is just really basic research for something as simple as atoms. And so when you go to the other fields where the qubits are even more complicated, we can't forget about the basic science. All right. One last thing I'll say about our work, and I'll go through this very quickly in the interest of time, is we're asking questions that I hope are very forward-looking. And one of those questions is a quantum functional group possible? Well, now, if you've had any chemistry, you may know that this term functional group. What it means is it's a group of atoms that you can attach to another molecule or a surface or something, and you imbue it with some function, like maybe it fluoresces, or maybe it binds to some other surface, or just some virus even. And the beauty of a functional group is that you design the chemistry of this thing such that you can pretty much stick it to anything and it still does what it's supposed to, right? It's like a little Lego block. And so our dream is, can you make a qubit functional group so that we can then go stick it wherever we want? And we've been working with these folks here. Wes, I've already introduced. Justin and Anastasia are two brilliant chemists at UCLA. Anna is a fantastic chemists at USC. And I'll go through this very quickly, but it's to say that we have found some chemical structures that look like, in fact, they may be these sort of qubit groups. And what that means is you can take the technology of today. So this is something our colleague Jason Petta does in collaboration with HRL, where they pattern electrodes to make man-made qubits, right? And then build quantum computers out of that. And instead of making these man-made qubits, which have some disadvantages in that, you know, they have hair, right? Everyone is a little different because we're making them. If you take this all the way to the limit of fabrication where chemistry is building your qubit, then each one will be identical, right? You know, every H2O molecule in the universe is exactly identical and indistinguishable. So if we can make our qubits out of these molecules, they will be exactly identical, reproducible, and perfect. Yeah, and you know, maybe you could even let chemistry be your ultimate to build your quantum computer for you. And so this is something we've been thinking about a lot. Okay, so I know I'm almost out of time, and I want to say one thing about stuff that's going on at UCLA and how it might interface with this group. So we have at UCLA the Center for Quantum Science and Engineering. A big part of what we do is hoping to build this bridge. It's a cross-division, cross-disciplinary organization. It has sort of 30 faculty or so that are focused on quantum at UCLA. We've been a big part of, you know, of different organizations over the years and really pushing quantum education. And through the CQSE, there's sort of three things that we're doing. The first was we established this master's degree in quantum science and technology as one of the first in the country. It's actually the first lab-based quantum master's program. And the idea behind this is if an industry is going to move to scale, it can't be all PhDs. And right now, if you go to any quantum industry, it's all PhDs. It's hard to hire them, it's hard to pay them, hard to keep them. We need to get, you know, a trained workforce more targeted there. And so the master's program is now in its second year, and we've been having a lot of fun, you know, helping our place our students and working with them. The other thing we're doing, and the fruits of this are here, has been leading a faculty hiring initiative to recruit experts from around the world to Los Angeles. These are the first fruits of that search or of that work, and we can expect much more to come. The final thing I want to announce, which I guess was announced maybe 2 weeks ago by Gavin Newsom in a press conference, is that UCLA has acquired the old West Side Pavilion Mall here in LA. Yeah. It was, I've been working on this for about 4 years, so it was quite nice to come to completion. And what we're going to do there is establish something called the Quantum Innovation Hub. And the dream of the hub is to get academics, industry, and government under one roof so we can work together to sort of, you know, make it more efficient, these sort of cross-disciplinary, cross-boundary collaborations that we struggle to do right now to really translate science out of the lab into the real world. So within the hub, we're going to have UCLA researchers, we're going to have industry, for example, HRL from Malibu has already, is already leasing, I don't know, a large portion of the hub. We expect to have some government agencies there. We will have an incubator there tied to a VC fund, and we want to run a industry consortium out of the hub to really catalyze and form the center of gravity for Southern California. And the last thing I'll leave you guys with was this picture from a couple weeks ago, 2 weeks ago actually, which to me is, having worked on this for 4 or 5 years, is pretty remarkable, because within this picture, this is President Drake of the University of California. This is Gene Block, the Chancellor of UCLA, and of course that's Gavin Newsom. And all three of these guys have come together around quantum as the future of UC, UCLA, and California. And so I think there are opportunities for partnerships, with Japan and nationally around this with UCLA. And I will stop there because I probably went over. All right, thanks.
Okay, I'm not a professor, but I just want to follow a lead and then standing up and present. So once again, my name is Kazu Gomi. I'm the CEO of an organization called Entity Research. My short presentation, I want to just to talk a little bit about where I am from, NTT, and then also that I want to introduce you some of the activities that we are engaged in terms of the quantum science and quantum computers. Well, NTT is a pretty well-known organization in Japan that incumbent, I don't like that word, but it is incumbent telecommunication carriers in Japan. But now, well, those who follow IT telecommunication, those converging. So it's quite kind of distance telecommunications without IT services. And so NTT is not, NTT is pretty much the same. We are now calling ourselves that the global IT companies. But in any case, one of the characteristics of NTT is that we've been spending quite a bit of money on R&D, which is a bit unique. We have presenters from IBM in the afternoon. Well, IBM probably certainly is a very reputable, good R&D organization they have, but well, from telecommunications, old time, used to be Bell Lab existed in this country, which not the same way that it has been. From NTT's perspective, that's that's sad. We try to kind of keep it up, our R&D spendings, and we are spending, putting a lot of focus onto it. So some of the numbers, I'm not going into details, but we still have quite a bit of R&D resources, and then quite a bit of the outcomes from it, patents, papers, and so on. So that's the organizations that from where I'm coming from. But we have a pretty long history of R&D, but one of the problems we realized maybe 15 years ago was that our researchers are mostly Japanese, and most of the activities are done in Japan only. And so in Japan, we are one of the probably most reputable R&D organizations, but well, is this where we should be, we want to be? The answer was no. So we have definitely an aspiration that we wanted to expand our footprints, and we wanted to work with the global talents, global partners to basically accelerate our R&D activities. Therefore, we decided to build this organization called NTT Research, which I am taking a lead of it. And we established this organization in California. Sorry, not in Southern California, but in Silicon Valley area. But that's where I am from. One of the characteristics, another characteristics of NTT is that, well, having R&D center in Silicon Valley, which is pretty much everybody does in the world. Just to look at the Japanese company alone, I can easily name 100, or probably maybe 200, quite easily. But most of the companies are really kind of has an aspiration to be immersed into the startup ecosystems and try to build new businesses, which is fine, which is great. But we try to do a little bit different thing, different tangent here. What we are working on is that we build a team to focus on the fundamental research. And then the reason why we do that is that, well, we can, first of all, I think we can afford it a little bit. And then it makes a much bigger impact for when you look at the longer time scale. So we decided to, once again, build this team about 4.5 years ago, and focusing on the fundamental research. And we currently have about 50 top-notch R&D researchers, basically top-notch researchers. And we are working on 3 areas of focus. One is, of course, today's topic, quantum science and the quantum application of quantum science to computations and communications and so on. And then just for your reference, two others, the next generation encryption technology, and then medical health informatics. We focus on, we call it biodigital twin. If I have a chance to talk about it, maybe sometime in the future. So, but anyway, so that's where I am. Now, let's just focus, change the gear to what we do in NTT with under the context of the quantum computers and so on. So I'm not going into too much in the weed, but the quantum computer, I think that the first fundamental idea came about probably about 30 years ago or more, longer than that, maybe longer than that. So you can call that is a new technology, but at the same time, it's been 30 years, 30 plus years. And then in realistic term, that there's not yet, usable practical machines available. So what that means is it's very interesting, very, very interesting, and very promising once you can get there, but it is super difficult, very, very difficult. And there was an article on IEEE's Spectrum, which is that reputable research society magazine, released a couple of weeks ago, actually, that the quantum computer is, once again, cool, very interesting, but it is very difficult. So it will take still a bit of a time. So when this is going to be practical, when we can start, people can start using it, God knows where we get, when we get there, where we get there. But I think that when you look at the situation right now around the world, there are so many people trying to do so many different ways. I think still nobody knows what is the winning equation is. So in a way, NTT is trying to do our own effort as well, but we are doing a little bit different way that, again, try not to go into too much of a weeds, but our approach is that, well, what do you want? Why do you want to work on the quantum computer? A practical sense. Of course, you want the more powerful computation systems. And then why do you need this more powerful computation system? Because there is a problem out there in the world that today's, even the supercomputer cannot resolve practically. So we want the machine which can resolve find the answer to the very difficult problem. It's with a much shorter period of time, and then maybe more importantly these days, with less energies to spend to get to the answer. So with that background, we have been working on this this machine called coherentizing machines. Probably nobody heard about this term, but this is, so again, skip some of the technologies, but the key ingredients of this approach is that the fiber optics and then the laser oscillators. And we have a lot of small light pulses going around this kilometers of fiber rings. And then there's a magic, and you can find some answers. All right, so answer of what? That's something you may want to talk about. So basically, our understanding, our recognition, that this is one of the problems that today's digital computer has a hard time to resolve, which is the combinatorial optimization problem. It's a kind of big word, but essentially what it is that there's many parameters, and then try to find the optimal solution, optimal set, optimal combination of the parameters. For example, well, this is a kind of like a textbook example here, but if you, thing called traveling salesman problem. So salesman needs to travel many, many locations. And then, of course, you want to find the most effective routes to visit all of the customers of the salesman. If you are talking about 2 or 3 locations, actually, you don't need a computer. You need only pen and pencil. You can probably figure it out without maybe 2-3 minutes, maybe. But the nature of this problem is that once that the number of customers in this case grows, the complexity of the combination grows exponentially, really quickly. So basically that's because there are so many different combinations out there, and so you have to kind of compare all the the traditional, well, most easiest way is just to figure out that what's the best, list it out all the possible combinations and then find out what's the most effective route. And then because the combination grow, that this computation becomes not very complex, but it's a lot of computations required. So this combinatorial optimization problem is, again, that's one of the hard problem for today's digital computer try to address. So, but I mentioned about traveling salesman problem, which is, well, I mean, salesman can travel without the quantum computers today. So there are so many other ways to do it in reality, but the similar problems are out there, like I mentioned, as you see on this slide, like drug discovery, and well, resource optimization is more like optimizing the routes and so on, similar thing. And the compressed sensing, which is basically try to find very difficult, like something like that, the black hole pictures in the universe, and then try to sense where the black hole is, that type of problem. And recently, getting more attention to is that this deep learning, of course, that's the AI. But these type of problem can be kind of transferred to that combinatorial optimization problem. And we are looking at the solutions, we're looking at the machine to solve these problems. And then once again, that our approach of coherentizing machines using fibers and lasers we believe that one of the shortest way to get there. So that's where we are working on. And well, this is a bit scientific, too scientific, but there's the number of the complexity of the problem on the horizontal axis, and the vertical axis is the time to get to the solutions. And typical theoretical quantum computer is on the red line on this side, and then the coherentizing machine is on the black line here. So in our kind of problem sets, that there are some promising results coming out coming out from our lab right now. And just to, as I started, from NTT's perspective, we wanted to work with different partners, different talents. So we are conducting this R&D activities by working with many US academic entities, as you can see here. And then actually we have some US Japanese universities as well. And we're kind of bridging them together and working on this. We believe that the very interesting approach to this very difficult computation problem and computation machines. Also, so, and I a little bit pivot a little bit. We talk, well, since AI is a big word of the day. These days, every day, I don't think you can day without hearing about AI. And AI is a great thing, perhaps. And then I believe if you can apply the AI in a good way, AI has much more potentials from here. But certainly there are many concerns on AIs. Of course, that the biased message and so on, that's one problem. And another problem is this, that the AI is basically heating up the Earth. And then maybe we can get boiled, which we don't want. So, and then this is the New York Times article that I found a couple months ago, that amazing thing is that based upon this prediction in 2027, that AI servers will consume the equivalent of electricity of the entire countries of Argentina or entire countries of Sweden uses. So that's kind of scary. So this approach that I show you, some of the pivot of that optical technology is that we see some of that kind of future that we can use those optical technology to potentially replace that GPU, which is the core of the AI engines today, and which consumes so much energies. By replacing the GPU with that, well, we call it analog mechanism, and a little bit of a quantumness into it, but that can basically lower the energy consumptions, and then we should be able to get the better or the same or better performance of today's GPU. So anyway, so that's the kind of things that we are working on at NTT Research. Again, that we are working with Japanese colleagues and the US colleagues all together, and then tackling with the big human problem. So I would end my presentation. Thank you.
So I'm not a professor or a CEO, obviously, but as a PhD student, today I'd like to do what a PhD student does best and just talk about my research. And hopefully in the next 10 minutes, I can give you a little introductory spiel about what I do in the lab, what our lab does in general, and hopefully that can give you a little bit of an idea as to where the field is moving, where the field is at right now, and where we hope to be in the next few years or so. So the Farron Lab in general, we work on, we had a very nice introduction about quantum computing. And if we can believe that quantum computing can be useful, I think it's straightforward to think that quantum networks can be useful. And so quantum networks in the most basic sense is just connecting quantum computers together. And we can think of it like just the regular internet where we like to connect regular computers together. We know how that is useful. So when we can connect quantum computers together, we can do all sorts of things. For example, we can distribute the load of the computation among multiple computers, or we can cross-check and check the answers from each computer through cross-verification. And so in general, we'd like to be able to connect different remote quantum computers together. And so the most basic idea and the most basic way we can imagine connecting two remote computers is to just hook up a cable between the two. And let's say we use a long coaxial cable. These things work at gigahertz frequencies, so like 5 to 10 gigahertz, let's say. But there's two very fundamental issues with this. And the first is that we actually lose about half the signal in just 10 meters or so. And the second more fundamental issue is that there's thermal noise. Room temperature is just much too hot for quantum information at this frequency. And quantum information is very fragile. And so this thermal noise at room temperature drowns out any quantum information that we might want to resolve or use for computation. So instead, the most straightforward thing we can do is just use an optical fiber instead. And we use these things in the regular internet as well, where these optical fibers instead work at optical frequencies, so like laser light. And these frequencies are a few hundred terahertz, so 200 to 300 terahertz. And instead at this frequency, we have two advantages. The first is that there's less loss. We only lose about half the signal in kilometer scale now instead of meter scale. And the second thing is, better yet, we don't have any thermal noise because the frequencies are so much higher, and so we don't have to worry about room temperature drowning out our quantum information. But there's still two issues with this. So the first is that we haven't completely eliminated the loss. We still have loss along the line, especially if we want to go to more than 10 kilometer scale. And the other thing is that one of the most promising platforms for quantum computing, the superconducting qubits, these work at microwave frequencies, so 5 to 10 gigahertz, which is initially why we wanted to use just a cable to hook them up. So we need to find a way to kind of resolve all these issues in order to make a quantum network possible. So one of the proposals to do this is what's known as a hybrid quantum network. So the hybrid is just trying to use different platforms and different frequencies to try to leverage the strengths of different platforms in order to make this connection possible. So again, we're starting out with some microwave quantum information at 5 to 10 gigahertz. And we want to use a long optical fiber instead of the microwave cable in order to hook this up. So the first thing we need is some sort of an interface, which we call a quantum transducer, in order to either convert or interface between microwave and optical quantum information. And to do this, it's not as easy as just reading the microwave information. Let's say it's a 0 or 1, and then we send it out in the optical domain. We can do that classically, but unfortunately, for quantum information, we need to preserve its quantumness. So we don't want to read it out. We don't want to mess with it. And so in order to make this conversion happen, we need to use some quantumness, or we want to preserve the quantumness. And so that's why we have to use a quantum transducer. And what we do and the Farallon Lab does is we use on-chip solid-state devices. So this is just one platform out of a plethora of different options that many groups across the world are looking into. But in this particular case, we use atoms inside of chips. And we talk to the atoms using these nanofabricated devices on the chip. So these are a few tens of micron scale, around the width of a human hair. And we have we talk to these atoms using these nanofabricated devices. And we like to use atoms because they're quantum. And so we can exploit the atom's quantumness in order to preserve the quantumness of the information while we do this conversion process. So further, we want to mitigate the loss in the system. So if we want to have a long channel between in the optical domain, we still need to boost the signal somehow. And again, the same problem with transducers. We can't just simply amplify the signal. That is kind of forbidden by quantum mechanics. So we like to use something like a quantum repeater or quantum memory in order to, again, use the quantumness of this system in order to preserve the quantumness of the information. And this is just a picture, again, a nanofabricated device of something the Farallon Lab has used to demonstrate a quantum repeater. And in this case, we can even talk to single atoms in these tiny structures in order to make this repeater protocol possible. And these are kind of both two technologically focused aspects into why we'd want to develop these quantum technologies. But one of the most exciting things I found about my research is that, as Professor Hudson mentioned, there's a lot of still open questions in quantum physics and a lot of fundamental things we don't understand, which came as a surprise to me, but it's a very open field. And one of the things that we can look at is, again, just fundamental science, fundamental physics. And from a technological aspect, we can, when we find new physical phenomena or new quantum phenomena, we can use that to our advantage and hopefully find new possibilities into doing things that, in a way that we didn't think before. But also just from a fundamental perspective, it's very exciting and interesting to kind of find out and dig into the real kind of quantum physics that's happening in the structures. And this discovery is really a process and a product of how we've kind of developed technology so far that we're pushing the boundaries of the parameters that we had before. 10 years ago, it would have been very, very difficult to make these nanoscale structures. But as we've developed the structures and the fabrication techniques and the understanding of our system as well, we're able to, again, push the numbers and the parameters into higher and better numbers. And in that case, we also discover kind of new physics in that way. So with that, I think that was all I had. So thanks for listening. And
All right, so I'll do the thing that most faculty don't like doing, which is just use words without slides or a blackboard. Thank you for having me here, Teddy and Jeffrey. It's been really fun to hear from the panel so far. And I want to note that in addition to a colleague being on the panel here, I also have somebody who represents my alma mater. So I'm really excited that both UCLA and Caltech are represented on the panel. And both institutions have taken a very thoughtful approach to interactions with industry, which is very important in quantum science and engineering. And that's something that I'll talk about a fair bit in the next few minutes. So in addition to being a faculty member, I wear a couple of other hats, and I do this because I feel like this is the juggling act I do pretty much every day. I am the Chief Technology Officer of Aliro, which is a quantum network company. So you set me up very well for talking about this. And a third role where I've served as US Science Envoy, and I'm very focused on quantum science and technology over the last year and change. So let me start with that, because as a science envoy, I had a chance to visit Japan, spend time there as a part of the G7. I'm looking at Celia because we were both there together and had a great time. Got a chance to interact with the Japan industry ecosystem, Q-Star. And one of the things that really stuck out, something that I think ought to become a topic of discussion here today, is a focus on applications driving advances in quantum technology. So almost all of the roadmaps that we looked at there were focused on what are the first applications. Every time axis there was about applications that are unlocked by various aspects of quantum technology. I use the word quantum technology because to me that incorporates quantum sensing, quantum computing, and quantum networking. So if you see that or hear that, and that's where that's coming from. And some of the earliest applications in quantum technology come from, of course, being able to predict materials and molecules better than we can, hopefully better than we can, using classical supercomputers. So when I started thinking about this problem, and when I was a graduate student, GPUs were pretty new, and most people doing electronic structure calculations, the types of calculations where you're working on these new molecules or new materials, we're just adopting GPUs as the backbone for how they'd go about it. Now, almost every DOE supercomputer, for Summit, now Frontier, uses GPUs almost exclusively. So to me, quantum computing is in some ways approaching that stage where we're thinking about how to incorporate both quantum and classical devices to predict something useful. But the focus is on predicting something useful and figuring out the best combination of these tools to actually get there. The promise of quantum computing in particular is around being able to predict molecules that are more correlated, perhaps than we can predict using large classical computers. And this is, of course, because we're inherently solving a quantum mechanical problem. We map it onto classical devices, right? So this would be a logical thing. We, instead of mapping it onto purely a classical device, we split up a part of the problem, map it onto a quantum device, put the two together, and hopefully get something that is better than those individually, right? This is something that lots of people in the field are working on. I and others have written about this. So some of these molecules or materials could form better catalysts. And that's of interest because almost everyone is looking for a way of doing Haber-Bosch better. Folks are thinking about how to have more green catalysts that don't use materials that you can only find in say, one mine in the world. We want to be able to do this scalably. And this is a pathway towards that. And I say pathway because, of course, there's predicting something new. Then ideally somebody, you convince an experimental colleague to synthesize it, and then it gets scaled up. So that part of the pathway still is long, but hopefully shorter than it used to be. We're thinking about new materials and how you can compute these using quantum devices. And this, I think, is a very good match. Types of materials that we work on in my group, in particular, quantum materials. These are ones where the quantum mechanical property dominates over, say, other classical things. I get asked this, what's a quantum material? How is it different from a regular material, which also has quantum mechanical properties? So yeah, here's the answer for you. So these quantum materials, and some of them are very strongly correlated and are a hopeless match for what you could do with, say, even all the GPUs DOE will provide you. But we are starting to see that some of these problems can be mapped onto small quantum devices. And hopefully, as the noise rates come down, as experimental colleagues across the world make progress in the field, perhaps we'll actually be able to do this scalably and of systems that are large enough to be of interest. Right now, we're solving smaller problems than we'd like to solve. So coming back to the original point for where I found the impact of quantum computing to best link with industry, I think this is an easy match. And as long as it's driven by that application, I think there will be a lot of progress in the near term. That was another question that I noticed has come up a fair bit and certainly came up during the G7 was how do we actually make progress in a time frame that retains the interest of everyone that is supporting quantum science and technology. And that's a question that most scientists don't like to answer because we like to think that there's seemingly infinite time and infinite resources that we'd be able to get to work on problems we're interested in. So being asked when will you actually be able to predict one of these exciting new materials? Give me a date, give me a year, I think was an interesting dynamic. So going forward, I think that there is, and hopefully something that we can discuss here is there is that push and pull. There's development of new devices, types of devices that are getting bigger and bigger. We've seen some announcements recently, as well as the problems we're trying to solve, and clever ways, by the way, of taking problems we're interested in solving and mapping them onto current devices. And that's the part that I'm really excited about, because I think that presents an opportunity to bring in ideas from applied math, engineering, chemistry, from physics, to actually be able to develop these new algorithms. You need that physical intuition to figure out what would be a good way to map the problem, but it's also very nice to have that mathematical toolbox to be able to solve these problems. So it's interdisciplinary and something that I think has something for everyone. Okay, so that was with my faculty hat on, and maybe a little bit of the interactions, the really fun interactions I had in Japan. Building on that, I want to mention some of the facilities we saw at the National Institute for Advanced Industrial Science and Technology, ICE, were really, really impressive. And something that stuck with me was a pretty big emphasis on doing device validation. So essentially, finding ways that if you make a quantum device and somebody else does, and you're talking about performance, to actually be able to agree on what is being measured. And that's something that could be a really fun area for interaction going forward, something that was discussed during the trip, and I look forward to reporting more on those lines in the near future. Let me spend about maybe a minute talking about the work that we're doing at Aliro, but more importantly, my experience translating a quantum technology out of the lab and some of the barriers that we faced. And since this is, I guess, a workshop that is focused on how we can have impact and benefit society, I feel like it's helpful to talk about those barriers, but also the things that went super well that can be replicated in other contexts. So there was IP that was developed in my lab, and that's really where Aliro started. And talented students like yourself said, hey, this would be great to start a company. Let's go out there and let's raise around. And I thought, oh yeah, with all the free time I have, let's go ahead and do that. But it's been a really rewarding experience to see how very fundamental IP that was developed in the group. It was not developed with an intent to be commercialized. It was, in fact, filing the IP was almost something that was an afterthought. It's not something that I do naturally with everything that we think about. But translating that has been really, really interesting. So now Aliro is bringing together both folks focused on quantum networks, as well as a larger set of people who know a lot about classical networks. And we're partnering with Cisco on making this a reality, because again, if we are to scale quantum networks, there's a lot of talk about quantum networks that are not just localized to small parts of the country, but actually nationwide. That's something that's going to require the kind of expertise that Cisco brings to the table. And we're really excited to partner with them. But it was a really eye-opening experience for me to work with a technology translation office at various universities, and to see how fundamental research and technology is seen by the university, and how one might actually overcome the slower timescale that typically a university has relative to how quickly industry is moving. And that's where I think initiatives like the Hub, which we've heard about from Eric already, as well as other centers across the country that are trying to make this a frictionless process, is incredibly important. So I'll stop there, and I look forward to many questions from the audience.
Thank you so much, Professor Narang, and to all the panelists. I will start out with one very quick question to get things moving, and then we will open it up to anybody in the audience or online. So a question for anyone in the panel, this might be best for Professor Hudson or Professor Narang, but anyone is willing to take it. 5 or 10 years ago, I think it's safe to say quantum technology was much more esoteric and obscure than it is today, mostly university work, whereas just in the past 5 or 10 years, we've seen everything from Ant-Man and the Wasp, quantum mania, to heads of state of very important and large countries talking about quantum technology, to, of course, the explosion of private industry effort, which some of you have already touched on and we'll get onto more this afternoon. So how has that changed the nature of scientific research in the university? Has that, I don't even know what that would look like. Has it changed the timescales or the emphases or the competition for talent, or is university research kind of still the same as it was when you all may have first gotten into quantum?
Please, go ahead.
All right. So yes and yes, and let me elaborate on that. When I got into this field, I don't think that I could have explained it in a manner that somebody at a social event would give me attention for more than 30 seconds. I would start saying what I do, and people will walk away. So they might still do that for other reasons, but now there's a lot of follow-up questions. Hey, could you explain this a little more? I'd love to get a coffee with you and get some answers. And that's something we're also seeing from the student side. So I, for a while, taught a course that was aimed at introducing quantum engineering to everyone who doesn't have a physics or a chemistry background. And a lot of students that took it were computer scientists and applied mathematicians. And their interest was, how quickly can we get to the algorithm and how to use quantum computers part. So I think it has changed the set of people at a university who are interested in this research. And that's a good thing. I think it's bringing new perspectives in. There are computer scientists who are now asking me about unitary coupled cluster, which is a very, very specific quantum chemistry concept. And I think that interaction has been fun. It has changed the pace. I think there is an expectation that there will be some partnerships with industry, that there will be some partnerships with these very large center level efforts. And I think, personally, it's my humble opinion on this, that's a good thing. I think it's leading to more collaborative science and moving away from, hey, here's my device, and that's all I care about. So we've seen that in the context of the big DOE labs, the National Quantum Initiative Centers. I'm part of the Quantum Science Center, and I interact with many more colleagues there now than I have in any other scientific interaction and collaboration. And that's not common, at least in my fields. I know it's common in other fields to have these large collaborations. And finally, it is changing the talent pool dramatically. The number of times I've had a postdoc say, nah, I'm going to take that Google offer. I'm going to go to IBM instead. And I asked them at some point, just out of curiosity, would you mind sharing a part of your offer letter? And I looked at the numbers and I was like, okay, yeah, there's no way. So I think it's changed the set of people we can keep in the field beyond the PhD. And even during the PhD, I've had a student who's taken a year off to go work at HRL. So it's almost changed the career opportunities. And in talking with senior colleagues, This in some ways resembles the time I wasn't doing science then, the early telecom days, where students would essentially very, very quickly enter a PhD and go to these jobs. I'll let Eric answer any part of that.
That was
I
a
didn't.
wonderful answer. Yeah, no, I sympathize with the postdoc problem. I think it is something serious to consider because, you know, postdocs are the ones that go become professors, and what do professors do? Well, they train more people. And so if we're peeling off all the postdocs, we're making less professors, we're going to train less graduate students. So 5-10 years, that bill's going to come due to industry. So maybe our industry colleagues can let us have some of their people. The other things I would, Pre's answer was fantastic. Just a couple things I might augment it with. One very positive, which is I have been astounded at what industry can do. I know in my own field, atomic physics, you know, we had demonstrated a lot of these things where they said, oh, in principle, you could go build this thing. But none of us really thought, like, hey, you're going to go do it. But if you go behind the curtain at these companies and you see what they've built, it's just so impressive. The technology is so much further than I thought it would be right now. And that gives me a lot of hope. I think in the next couple of years, we're going to see machines that can do things that can't be done on any classical machine with high fidelity. I think the impacts there will be that I see are primarily to physics. So doing things that I care about. I don't know how those will go outside of the industry, but I think in a couple of years, industry is going to deliver, and I think that's fantastic. The sort of opposite side of that same coin is, you know, the things that industry delivers may not be what the world thinks they were promised. And that is, you know, that's kind of my worry. And one of the things that, like, as an academic, I don't want to be like the Debbie Downer at the party, but I just kind of want to be like, hey guys, you know, this might take a little bit longer, you know, politicians, if we don't deliver this in 3 years, like, you know, maybe think that it's a 10-year horizon, not a 3-year horizon. And I think that's naturally the role of academia. So, you know, it's forced us all into roles that none of us were prepared for or even good at, but it's been fun.
Thank you.
Yeah.
Is there anybody in the audience who'd like to ask a question? Yes, back there. You can just wait for the microphone. Thank you.
Hi, my name is Richitras. Thanks for having us here. My question is, how do we communicate a quantum notion to a piece of hardware? Do you mind giving us an example? And what would be an example of an extreme quantum demand, regardless of our ability to carry it out? Thank you.
You might need to unpack that question a little bit more.
Essentially, it's trying to bring definition to quantum and how we as humans can communicate with something in a quantum manner. Because I'm assuming we would just speak to something normally and then expect it to deliver quantumly or something. And you spoke a lot about Professor Prina, sorry if I mispronounced. You spoke a lot about predictions. So I'm wondering what kind of predictions you are aiming to figure out with quantum hardware, and if you're speaking about the future, if you're also trying to use quantum to predict things. I mean,
so if I may reframe your question, perhaps you're asking what types of problems are we mapping onto current quantum devices and how we're going about it. Okay, so a lot of the questions and problems people are interested in essentially are quantum mechanical in nature. So, right, when we're thinking about, say, one of these molecules, you're thinking about, say, encoding the full wave function. Now, you don't want to do that. That's something that would be a really, really hard problem. Instead, you pick parts of the problem that are tractable, and you map that onto a quantum device. And how you do that mapping essentially depends a little bit on the type of technology you're working with. So if it's say something that has all-to-all connectivity, and that'll be something that Eric can speak to, or if it's a superconducting device where it's not necessarily going to be all-to-all, but there are ways you can do the encoding. So essentially, you start out with something that is a simplified mathematical problem, and you map it onto yet another mathematical problem, which is more in circuit notation. In this case, treating it as a quantum circuit. And that kind of mapping and being able to actually compile the problem or transpile the problem is something that a whole set of people are also working on. Yeah, so hopefully that got your question.
Thank you. Any other questions from the audience? Yes.
Thanks. I have a question for Professor Narang. So as a science envoy, how's the State Department balancing national security with this issue of global collaboration and a shortage of talent? Like, I just would see how you're seeing things as a science envoy.
All right, so let me preface the answer by saying this is my personal opinion and doesn't represent the views of the state. So the fact that a science envoy in this field was designated, I think, is already a sign that there is an interest in figuring out how to interact with and thoughtfully establish international collaborations on quantum science and technology. And a major focus of that has been talent sharing. So having students, postdocs across countries find ways of, say, spending time in one country, spending time in another, bringing the science and technology cultures of those different institutions together. And that's something that's being talked about quite extensively, and how do we lower the barriers to doing that. And in terms of training new talent and thinking about how that can happen in a way that we're not all fishing in the same pond is also another factor that's been discussed in almost every roundtable I've been involved in over the last year and change. Yeah. So it's front and center, I guess, is the point.
Thank you. Do we have a question from online, Nick?
Yes, we do. A bit of a two-part. I'm consolidating some of the questions that we're seeing. And it's, I think you can all answer it because it's just a few words from each one of you. What is, in your opinion, the most promising quantum algorithm these days? And it's a bit of a two-part. In which field of knowledge, human knowledge, can quantum make a near-term impact? Would it be chemistry? Would it be physics, finance, medicine? And to link it to the title of today's presentation, how can it make the world a better place? So would it be QAOA, VQE?
Let's start.
We'll go down the line.
So
a few words.
yeah,
A few
okay.
words.
So I think the most interesting thing is what I would call Hamiltonian simulation in the near term. It turns out that certain problems are hard to understand in the universe, in quantum mechanical problems in the universe. And that is problems where you have many different bodies interacting. And that has to do with exactly the structure of quantum mechanics that makes it really hard to put that on a classical computer. On a quantum computer, it's much more natural. So I think it's already happening. There's some great results. I think in the next 2 years is when it's really going to hit, that we're going to be able to simulate physical systems and understand their behaviors in ways that we haven't before. And my hope is that what will emerge from that are like what you might call emergent theories, like hydrodynamics. It's like not really a microscopic theory, but it's a theory that explains stuff. So if we get a hydrodynamics of entanglement, that will allow us to better understand quantum systems.
So yeah, I mentioned in my presentation a little bit that in terms of the applications that certainly the material science and chemistry, there's a lot of activities going on, and I think Pri mentioned it also there. But I definitely think that given all that the things going on and AI and all that, that quantum may be able to apply to the AI machine learning areas, that we can really expedite the machine learning process, and then really at the end of the day, more energy efficient solutions might be possible. So that's certainly the emerging areas, at least to me, for the last couple of years. And then seems like that is drawing a lot of attentions in the industries for obvious reasons.
Yeah, just to echo what Professor Hudson was mentioning, I think my favorite field is many-body physics. So as he mentioned, when you put a lot of quantum particles together, we can't really, we don't really know what to expect. We don't know what's going to happen. And using these, our improving technology, we can probe more and more into how these systems act together, how these systems work. And it's not only fundamental, but it can, again, give us insight into how we can implement these technologies. So I think in general, many-body physics and its applications are very interesting.
Yeah, not much left to add, but yes, simulating many-body problems is something that's near term. There has been a lot of interest in how various problems in finance can be mapped onto quantum devices and how they might be a near-term advantage. I'm waiting to see some of the big results emerge there. So, yeah.
Thank you. Any other questions? Yes, in the back. Oh.
Question regarding how quantum computing can be helpful in terms of like drug development. As we know, like small molecules or peptides, the binding site and structure is very important in the efficacy of a potential drug. What are your insights in this? Thanks.
I'll field this.
If you want.
So very recently, in collaboration with some of the folks on the life sciences side and other colleagues, we've been thinking about oligonucleotide structure-function relation. I should preface this by saying I have a physics background. I'm not a biologist, but we've been thinking about how you could essentially take parts of the problem and use ideas in graph theory to actually tractably solve this problem. So there's a subfield of a subgraph isomorphism that essentially we've been leveraging in this domain. I'm happy to talk about it in more detail. Essentially, if the high level answer would be, these are very, very large molecules. So when I talk about small molecules, I really count the number of electrons or not even number of atoms that we're interested in. And folks who are talking about some of these larger, say, RNA-like structures are thinking about something that's massive. But maybe we don't need to solve the entire problem and just a piece of it. And even that piece, we've been kind of thinking about how, subgraph isomorphism can help. Yeah.
We'll say at least it will be helpful. We'll say at least it will be helpful in terms of like simulating the binding sites using quantum computing.
So we and others are trying. I think that results that conclusively say we've learned something that you couldn't have or didn't know otherwise are still a little ways out.
Thank you. Maybe another question from online.
This one is for Mr. Fukumori. What do you see as the greatest challenge that today's emerging quantum telecommunications companies will need to overcome? Is there something the industry is optimistic about?
I think it's probably to Mr. Gomi.
Yeah, sure. Maybe I can answer that. Obviously, yeah, quantum internet is the word, but of course that you need, at the end of the day, you need to have a quantum computer to run the internet. You need a router, and then the router is a computer at the end of the day. So to create the quantum computer, quantum network, quantum internet, such thing is possibly maybe 30, 40 down the road. But the most important ingredient is that the quantum routers, and effectively that is a quantum computer. So those are the building blocks. So, but once that is done, potentially that the existing fibers and all that can be used and so on. So yeah, definitely the most difficult part is how to come up with that effective quantum router / quantum computers to get there.
Thank you. Any other, in the front row? You just wait for the microphone, please.
An order of magnitude question. You mentioned the electrical consumption. How much more efficient is quantum computing likely to be than current computing? And or how quickly can a quantum computer mine a Bitcoin, and will we be all done?
obviously, that's actually a hard question to answer, depending upon what type of problem you're talking about, right? So, well, and then also that the type of the structure of the quantum computer you're talking about. It's all kind of all different maps is possible. But at the end of the day, I think that the quantum computer will be, well, today's digital computer is such that it is very useful, right? Most of the people think that it is working. And so quantum computer will be used for some specific, very difficult problem, like molecular analytics or some AIs and so on. So for that particular problem set, we believe that if we do it right, a quantum computer can do order of magnitude wise, it's probably 100th, or that is basically a percentage of the current energy usage to the quantum computer. That's what we believe that we can get there. But another kind of trick is that, again, depending upon what type of quantum computer you're talking about, some of the quantum computer, as you see some of those, pictures here, this picture is, well, part of quantum computer, but I believe this is the thing called dilithium fridge. Basically, this is the refrigerator. And so quantum mechanism itself, energy consumption is probably not much, but to really cool it to the so lower temperature, this requires so much energy. So when you think about that piece, the whole equation is broken. So we still have a number of things need to be done. And then again, there are, I think, a big discussions just possible just for that topic. But that's my kind of long answer.
Thank you. If I could just ask a question from the stage, you've all touched on this, which was great in your main comments, but when it comes to basic science research, what is there cooperation between the US and Japan? What exactly does that look like? So is that, exchange of people? Are there direct collaboration at individual labs working and co-publishing together? Is that mostly organic? Is that happening at the sort of organized government to government level? What opportunities for promising co-research between the US and Japan do you all see?
So I think I can just give an example from my experience. I'm part of a fellowship, and I think a lot of Japanese students in the US as well are on some form of fellowship from Japan or from other organizations. And one of the fellowships I'm a part of is the Quad Fellowship. It's kind of a international collaboration between the US, Japan, India, and Australia. And we're kind of working on a paper together to kind of put these things into perspective, how we can, as a young workforce, try to amp up the collaboration as the workforce grows. I've seen it myself in PhD. I think, my senior students, like 6 years or so, they didn't really get that many requests from undergrad students to work in their labs. But then, this summer, just in a few months, I've gotten so many emails from undergrads interested in working in the quantum field. So as this kind of workforce grows, we want to expand and try to have venues for collaboration. And I think one venue is fellowships, at least for the young workers.
Thank you. Any other questions from the audience? Second row, wait for the microphone.
In the fall, the Getty Museum is sponsoring an initiative called Art and Science Collide. And I'm curious if any of the panelists have the ability to speculate on how quantum computing might be utilized or influence the arts in coming years. Thanks.
Everyone's looking at me. So that's obviously beyond my expertise. I guess just what I would say, just as a fan of the arts, it seems that quantum is, and the concepts of the ideas of quantum, superposition, entanglement, like they are no longer just things that I talk about with my friend, with my colleagues, but my friends and family want to know what they are. So I think these concepts will spread to our larger population, and maybe that'll show up in art. There's, it's an interesting way of looking at the universe once you kind of understand what's going on. So yeah, maybe that'll feed back to art.
Just a quick word about that. At U Chicago, my undergrad, there's a lab called the Stage Lab. Professor Nancy Kowalek, I think, she looks at the intersection between art and most recently, I think, quantum physics. So I think, if you want to check it out, Professor Kowalek's work is very much the intersection between art and science in her lab. Yeah.
Thank you. Maybe one more question from online.
Is there a strategy as quantum becomes more and more advanced to democratize it and sort of move on from graduate expertise from graduate level to undergrad and even to high schoolers?
Want to start?
Please.
No.
Oh, me?
Yeah.
Oh. So, I mean, there's obviously, so within the National Quantum Initiative in the US, there's a large push for workforce development and quantum education. Those of us that are in the field right now and are educators, we're most comfortable teaching graduate students and undergrads. And so that's why you see things like, the master's program that we created. That's sort of a new effort that we can launch, and we know how to teach those things. There certainly are efforts within the country to go, K through 12 and other places. I am honestly not qualified to do that. So I think that those things will happen later. There are people working on it, but my opinion is we train what is closest to us first and let those people train down. So there's efforts in the country, and I think it will happen. Yeah.
Just to add, there is an APS, American Physical Society program, Quantum on the Go, that aims to send people into classrooms and an AP physics classroom, for example. So I did one of those, and actually a classroom that was an hour and a half away from UCLA. Didn't realize that when I signed up for it. And got a chance to communicate. And I think students that have some background in physics that they've taken as a high school student, they can pick it up pretty quickly.
Just as a little bit of background, the National Quantum Initiative is the result of a bipartisan piece of legislation passed by Congress in 2018, currently up for reauthorization, which has a big workforce component to it. So this issue of quantum workforce is something that has reached the highest levels of the US federal government and other nations' governments as well. Maybe in the second row here.
Yeah, thank you very much. Great panel discussion so far. I would like to mention just two things before I ask my question. At UCLA, there's an art and science program that's phenomenal.
Okay.
Victoria Benson, I think, and there was a gentleman in the nanotechnology that did a lot of work with him. And workforce education, K through 12 stuff, that's something that I've been very involved with for a number of years, and community college as well. So when those types of things come up, to your level, if you can provide any expertise, particularly I like to work with university students in their clubs to go out to high schools and encourage that. My question is about the, I'll say networking, but both quantum networking technology and ecosystem, like in Southern California. So many other areas around the globe, in this country and elsewhere, have very nice quantum ecosystems that have evolved. Some of those have physical networks that they're building. And how could we help make that happen in Southern California?
So that's a large part of why the hub, that's what the hub hopes to do. What I will say, if I may, because I love LA, we're really fortunate. Like, we may not quite be as organized as Chicago, but most of the quantum companies are in California and Southern California. So we have a big leg up there. And so I hope that the hub is gonna do exactly that.
There are smaller social
That's true.
Events that happen. There's a quantum beers that, the beer is real and the discussions are quantum. So there is an effort for scientists and folks here locally. And we sometimes, in addition to folks from Caltech, UCLA, and the companies nearby, also have folks from Santa Barbara who are there, Station Q, and it's a fun event. So.
Yes, in the back row.
Hi, thank you. This was very informative talk. I am an artist, so I have my interest in this is coming from an interest in art and psychology. And I guess my question would be, as we're on the advent of, another incredibly major shift in communication and psychotechnologies, using quantum for communications, it makes sense that it would be harnessed for security reasons and industry. Even the title of the talk today is harnessing it. So I guess my question is, as this is becoming real, more and more real, and there's so much funding for it, is there, in this pie chart of interest, is how much is being built in simultaneously to discuss ethics and environment, as it's been really important to hear that that's been mentioned. Sorry, I'm nervous. I'm not a great public speaker, but I'm asking more of a layman's question about the ethics behind all of this, as we're going to just
Government.
into a whole nother thing. And I've watched programs about this and about security mostly, and new ways of maybe even waging war. So I'm kind of interested in the ethical conversation and environmental responsibilities and how that's been impacting your research, or if it's this new hub, if there's going to be a whole new wing about that, because it seems to me that we put those conversations always come last. And that's why we're in a lot of the positions we're in today. Thank you.
It's definitely your question. You're like
I guess-
literally the science envoy.
Oh, okay. Yeah,
Okay.
so, the ethic questions is, and then social responsibility, I guess that's your questions, right? That, yes, we all have to worry about that. And when it comes to, I think AI certainly kind of brought that, the topics to the surface level very, very quickly. And then I kind of realized everybody that you really have to think it through. So I think it's a kind of elevated to the next level, good and bad because of the AIs. That's what I feel like. Of course, that when it comes to the chemical, pollutions and all that kind of stuff, that has been out there for a long time. And then pretty well, in a way, the chemical waste and all that kind of stuff, that has been out there. And then, so we have a pretty well established standard and the regulations and so on. Now AI is a new stuff, and then there's no regulation, therefore everybody's freaking out and then kind of running around. That's where we are. But I think that the people will find a way to do it, like we did for the chemical waste and so on. That's kind of like a very quick answer to you, not very elaborated, but I don't know if I answer all of your questions, but that's how I see it.
Anybody else want to take that one, or should we go to the next question?
Well, I'll just add that I think it's something that a lot of focus has been on the impact of quantum technology, and some of it has environmental impact, very positive impact. I recently received support to think about quantum sensing, particularly in the environment, thinking about how we can learn more about the atmosphere and aerosols better. That's something, we think about air quality a lot in Southern California, but also how these sensors could tell us something about the moving parts in climate models. So, there's a lot of positive impact, and perhaps something that the fields could do better is communicate that positive impact more broadly. So thank you for bringing that up.
Yeah, I'm trying not to say too much here, as I'm just the moderator, but I'll mention that one application I've seen of quantum simulation is for improving direct air capture of carbon dioxide in the atmosphere, among many other environmental applications, also things like improved solar panels. So I think there's a pretty strong case to be made that quantum computing may be a net benefit to the environment in several different directions. Nick, should we go back to the online questions?
One for Professor Hudson. What has been the biggest challenge in bringing academia, government, and industry together?
It's a lot of cat herding.
Yeah.
But we're fortunate. It was the hub was a bottom-up effort, so it really started with the faculty, which you might forgive me for saying that probably means it was a good idea. And, we had to take it to the leadership, and we were just fortunate that the leadership, all the way to the governor, fell in line, but it was just a lot of convincing.
All right, I hope people are hungry, so I'll maybe one or two more questions. Yeah, over here in the corner, maybe.
Hello. This is a question that comes from a person with no science background. So when I was listening to your panel discussion, I was imagining putting myself in an imaginary world, what kind of world I would be living like. So when I was a kid, no answering machine. My parents didn't know where I was, but I would come back home by dinner time. So that was that. Right now, speeding forward, I have cell phone. Siri wakes me up. I can track my daughter where she is. I can use my AI as my therapist. So that's the world I live in. So with quantum technology being applied to this world, I won't hold you to it, but I am imagining what kind of world I will be living in. So if you could just paint the story for me, that would be great.
It's a great question. Thank you.
Perhaps that again, I point out potentially, right, that that drug discoveries and all that kind of stuff is one of the most probably impactful areas for everybody's life. So, well, I don't know. God knows. Hope that doesn't happen, but the COVID-29 happened. We can find that the vaccines much more quicker, or some other diseases. Those are certainly perhaps I can point it out that without thinking much. Anybody has any other?
I'll just add that the applications of quantum networks and unconditionally secure communication hopefully will present us with all of these your password has been compromised scenarios going away. And that would be a good thing, because the number of times I've received that is getting to be too many. So.
Maybe time for one more question. Yeah, in the back, standing up.
Hello, thank you. My name is Adar. I'm a UCLA undergrad, Berkeley Law, Berkeley Center for Law and Technology, and three-time International Association of Privacy Professionals, privacy manager. I had a question regarding privacy. What do we think with the advent of quantum computer programming, quantum data processing, how will that change data privacy from a consumer perspective? And then secondarily, do we think that there might be a need for a higher standard for data privacy when it comes to quantum processing?
So probably there are a couple of steps before that. And I think some of the panelists here probably pointed out, but maybe you are aware that quantum computer, once that is quantum computers available, that the public key based encryption system can be broken very easily. There's a thing called Shor's program algorithm, which is basically the key to break that today's public key encryptions. So that's more like a downside of the quantum computers in a way that so a lot of industries has realized, and then in the United States, and NIST has already published that new algorithm, cryptography algorithm, to basically go against the quantum those problems. So a thing called post-quantum encryptions. So that's a step one, I guess. You just have to fortify what you have been doing to protect your data and the privacies. But I think the future potentially is that if the real quantum computers are out there and the quantum communications is in place, that the security actually is going to be a lot higher. That something data being copied from A to B today's digital technology, you can do it without much of a problem, and then that's good and bad. But with the quantum, that is basically impossible. So, so data security is going to be brought into the next level once everything is going to be the quantum world with the networks and everything.
So we are going to bring this panel to a close. If you could please join me in thanking our panelists.